Okay, so now 7-8. 7-8 is about convolutions. So convolution is an operation that you do on two functions. So addition, for example, is an operation you do on two numbers. Take two numbers, you apply the operation of addition, and you get a new number. So convolution, you take two functions, and you apply this operation of convolution to get a new function. The notation for it is a star or an asterisk. So f star g is the convolution of f and g. It's a new function, so I have to tell you what is f star g of t, and here is the formula. It's equal to the integral from 0 to t of f of t minus v times g of v dv. Okay, so let's look at an example. Let's take f of t equals t and g of t equals t squared, and we'll figure out what their convolution is. Okay, so I just write down from the formula here, the definition. It's the integral from 0 to t. I need f of t minus v, so that's just t minus v, times g of v, so that's v squared, and I integrate dv. All right, now just multiply that out. So I have tv squared minus v cubed dv. So that's t times 1/3 v cubed minus 1/4 v to the fourth, evaluated from v equals 0 to v equals t. So that's going to be 1/3 t to the fourth minus 1/4 t to the fourth minus 0, which simplifies to t to the fourth over 12. So t to the fourth over 12, that's the convolution of t and t squared. Now, if you look at the definition, g star f doesn't look the same as f star g. So it's not obvious that they should be the same, and maybe they're not. It turns out that they are, but it's not obvious, so let's derive that. Let's look at g star f of t. Applying the definition, I have that it's the integral from 0 to t of g of t minus v times f of v. And that looks different from the integral defining f star g. But now I can do a substitution. So let me substitute w equals t minus v. So remember here, in that integral, t is a constant, v is the integral of integration. So dw equals negative dv. And my integral becomes g of w times f of, well, v, if solving this thing here for v, we get v is equal to t minus w. So t minus w. Dv equals negative dw. And then I have to change my limits of integration. So for the lower limit, v equals 0 becomes w equals t minus 0. So there's t down here. My upper limit, v equals t, becomes w equals t minus t, or 0. I can get rid of that negative sign by swapping the limits of integration. Instead of going t to 0, I go 0 to t. And then inside my integrand, I just have ordinary multiplication. It doesn't matter what order we do that in. And that right there looks exactly the same. That is, by our definition, that's f star g. So it turns out that f star g and g star f are in fact the same, even though it might not be obvious from looking at the definition. In other words, this operation of convolution is commutative. And that's the first in a list of properties that the convolution has. So let's write that down. F star g is equal to g star f. It's the only property that I'm going to derive here in these videos. So the other ones I'll just list, and they show you, some derivations in the book. You should read those. Okay, so f star g plus h is equal to f star g plus f star h. So it's distributive. It's also associative. If I do f star g and then the convolution with h, it's the same as if I take the convolution of f with g star h. If I take the convolution of f with the zero function, I get the zero function. And the fifth property, which is the most important for us, for our purposes here in this course, the Laplace transform of f star g is the product of the Laplace transforms. Okay. And this is an important one for us. I'm not going over the derivation. It is in your book, the proof of the convolution theorem. It's on page 399. You should read that. And we could talk about it in a live session, office hour Q&A session later, but I don't want to spend time in these video series going over it right now. But that is our most important property for us in the solving of differential equations. And frequently we'll use it in the other direction by saying that the Laplace transform of a product is the convolution of the Laplace inverse Laplace transforms. Okay, so let's do an example. So y double prime plus y is equal to g of t. Y of 0 equals y prime of 0 equals 0. And we don't have an expression for g. Now, g is just a generic right-hand side to this non-homogeneous equation. So we take the Laplace transform on both sides. The Laplace of y double prime plus capital Y of s is equal to capital G of s. Using my rule for Laplace of derivatives, I have s squared times capital Y minus s times little y of 0 minus little y prime of 0 plus capital Y is equal to capital G. In this example, y of 0 and y prime of 0 are both 0. Solving for capital Y, I get 1 over s squared plus 1 times capital G. So it's a product of two functions. So let me call that first factor capital F. And we can get just straight off of our table that the inverse Laplace transform of capital F is sine of t. So I can call sine of t, that's my little f. Now my rule that we just found says that L inverse of capital F times capital G is equal to the convolution of little f and little g. And of course that's L inverse of capital Y. So my solution, y of t, is the convolution of f and g, which I can write, according to the definition, it's the integral from 0 to t of f of t minus v times g of v dv. And plug in for f is sine of t, integral from 0 to t of the sine of t minus v times g of v dv. And that's our solution. So if you come back and you look at this, is a very generic example. So if you have any initial value problem that looks like this, and it doesn't matter what that function g is, you can write down the solution by using this box formula, using this convolution. All All right, let's do another similar example. Y double prime minus y equals g of t. And this time y of 0 and y prime of 0 are both 1. Okay. Then we have Laplace of y double prime minus capital Y is equal to capital G. So I have s squared capital Y of s minus s little y of 0 minus little y prime of 0 minus capital Y equals capital G. Y of 0 and y prime of 0 are both 1 in this case. So I get s squared minus 1 times capital Y minus s plus 1 equals capital G. Solving for capital Y then, I get s plus 1 plus capital G of s divided by s squared minus 1. We can split that up as s plus 1 over s squared minus 1 plus g of s over s squared minus 1. That first fraction we can simplify by factoring s squared minus 1. Factor it as s minus 1 times s plus 1. And we have 1 over s minus 1 plus 1 over s squared minus 1 times capital G. And let's call this factor here, that's my capital F. All right, then if I do the inverse Laplace transform to get my solution, the inverse of 1 over s minus 1, we read that off of our table, or just remember it, e to the negative t. And then I want the Laplace transform of this product. The Laplace transform of capital F times capital G is the convolution of little f and little g. But what is little f? Now I need to figure that out. Okay. So I want the inverse Laplace transform of 1 over s squared minus 1. I can use partial fractions to write this as 1/2 times 1 over s minus 1 minus 1 over s plus 1. And then we can read off the inverse Laplace transform from there. I've got a factor of 1/2. Inverting 1 over s minus 1 gives me e to the t. And inverting 1 over s plus 1 gives me e to the negative t. And you could leave it like that, but you may recognize that that is, in fact, the definition of the hyperbolic sine, or sinh. So f of t is sinh of t. And if you didn't know that, if you haven't learned that, if you've never seen that, that's okay. You could just leave it as 1/2 times e to the t minus e to the negative t. It's the same thing. All right, then what do we get? Then I can put that into my formula for y of t. I've got e to the negative t plus, and now I have a convolution. So write the definition, integral from 0 to t, f of t minus v. So that's sinh of t minus v times g of v dv. And there's a general solution to any problem of this type. Let me go back to the beginning. Any g you want now, if your initial value problem has this form, then you can find the solution by plugging that function g into this integral and writing down your answer. Okay, and that's the end of this section. Also the end of our coverage of Chapter 7. We're going to continue with Chapter 8, Section 8.1. We're going to do maybe one more video in this series. So I'll see you then.